into orbital diagrams today, and then we'll finish up the rest of the section. So going back to electronic configurations, remember that we had our little diagram here that we used as a kind of a cheat. Did you just look at it? Yeah, I can't remember. No. No. Okay. My goodness gracious. Okay, and it didn't have 60 or 6 step, right? It just stopped on 60.
Yeah, it stopped.
Okay. It's easy to figure out that you can go further on than that because there's more elements than there are places for electrons here, but we're going to stick to the Okay, so remember that we have this little cheat here that we could use in order to figure out the order that the shells fill. And remember that we did this going in order of these diagonal lines. So we had our order that we filled the orbitals, and then we did some practice problems. So let's just kind of refresh our memories a little bit, get back into this. Let's just pick one arbitrarily. What element do y'all feel like doing? Calcium, is that what I heard? Okay, calcium, sure. So calcium, how many electrons does calcium have? 20. Okay, so where do the first electrons go? 20. The 1s, how many electrons can go in the s orbitals? 2. Okay, so where are my next electrons going to go?
2s2.
2s2, and then my next one?
2p and 6.
2p, and we can put 6 in the p orbital, so we have 6 there. Then where?
3s2.
3s2, and then what? 3p6, and then lastly we have what? 4s, how many? 2. Okay, so remember how to use these arrows. You go down, you fill them in the order coming from the top to the bottom of each of these arrows. S's can have 2, P's can have 6. How many can D's have? 10, and how many can F's have?
14.
So you know that stuff. You should be okay when you're doing these. This should be, hopefully, a lot easier than doing stoichiometry. So this is our electron configuration. Now, along with electron configurations, we also have what are called orbital diagrams. What is the difference between an electron configuration and an orbital diagram? So look on your outlines. I remember. I think this is a specific question.
It is.
Yes. What is the difference between the two of those?
Do they show the spin?
Orbital diagram shows spins. What else do they show? When you're drawing orbital diagrams, are you writing letters like this? What are you writing?
No, you're drawing.
You're drawing the electrons in, right? And what do you have to do for like the p orbitals? What do you have to do? Do I just do one big p orbital like this?
No, you do 3.
I split it into the 3 separate p orbitals, right? So I have my 3 p orbitals. How many d orbitals would I have? So we have 10 d electrons possible. So how many orbitals is that? 5, right? Yeah. So I'd have 5 d orbitals and how many f? 7. Don't worry, I don't usually make you draw out d and f orbitals. That's a lot of work. So our electron configuration, this is kind of like a general picture as to where the electrons are. When we get to the orbital diagrams, we're looking at what electrons are in which specific orbitals. So for example, let's pretend we want to do the orbital diagram of this one. When I do my orbital diagrams, the way you start this is, I always recommend, if you're asked to draw an orbital diagram, write out your electron configuration first. That will give you your idea of what you actually are going to use. So you write out your electron configuration, then you can draw out the actual orbitals down here for the orbital diagram. So like my 1s, I just drew a line, put 1s under, 2s, drew a line, put it under. 2p, I have 3 separate lines because there's 3 p orbitals. I do not make you write down px, py, peasy. I don't do that in this class, so you don't have to worry about those. If you want to, that's fine, but you don't have to. You can just draw 3 lines and put 2p, 3p, whatever underneath it. So here's my 2p's, here's my 3s, here's my 3p's, and that's my 4s. This is what I'm going to be using. Now, to fill this out, what I do, well, first of all, how many electrons can go in each of these orbitals? 2. So I'm going to fill them up 2 electrons per line. That's the kind of the concept behind here. So I go through, I say, okay, my 1s has 2 electrons, so I draw my 2 electrons. 2s has how many electrons? 2. So I draw my 2 electrons, right? So now notice when I draw them, I have one spinning up, one spinning down. Spin should always be opposite. You don't put them together. If they're spinning the same way, there's a lot more repulsion, and they would just kind of spin apart. So when the electrons are sharing the same orbital, they're spinning in opposite directions. My p orbitals, for this one, it doesn't really matter because they're full. But when you fill in p orbitals, it's good practice to put 1 electron in each orbital and then go back through and pair them up. Why is that a good idea? There's a term that you defined last time that explains this. And what does Hentrel say? You go in and each of those suborbitals gets 1 electron first, and then you go in and pair them up. Why do you think if you had 3 electrons, let's pretend you have 3 electrons in a p orbital, why are they going to be like this and not like that?
Then it would change
What do we know about the physical properties of electrons? We kind of talked about this last time. What do we know about electrons? What are they? Negatively charged. Okay, so I have 3 separate p orbitals. Here I have 3 of them, 1 in each orbital. Here I have 2 and 1, and I have 1 here and none there. Why would it choose this over that? They're farther apart. So here, they're farther apart. You have, remember we have our p orbitals have all those different directions and everything. They're pointed in different, they look different. So you have them further apart. Whereas here you would have 2 in the same one, so it's more crowded together. So it minimizes that repulsion by spreading it out in each of those orbitals first. So when you're filling these out, when you don't have a full p orbital, it's really important to make sure that you put them 1 in each one and then go back and pair them up. Okay, back to this one. We have 3s. How many electrons are in our s? 2. And then how many are in the next p? 6, right?
Sorry.
Okay, just making sure. And then how many go in that 4s?
2.
Is everyone awake, or is just like my front row here awake? Just the front row's awake. I'll just start scaring you all about outlines being due again. You're not getting the reaction. Okay, so this is the orbital diagram for calcium. So the orbital diagrams are a little bit more entailed. They take about a minute longer to write than the electron configurations. But they show you the spins, they show you how the electrons are paired, so you can see kind of the repulsion that's going on with them. So that's the difference between the configuration and the orbital diagrams. You are expected to know how to draw both. So you do need to know both of these for the exam. And I'm 99% sure I'm going to make this one a short answer because I don't like multiple choice with these. I like you to have to draw these. And our classes are dwindling in size, so I think we're getting to a number that's feasible. Okay, any questions on that? All right, so I think that we have, let's see here, what's the problem? The orbital diagram for magnesium. You're supposed to do, magnesium has how many electrons? It has 12 electrons. And what is the first thing I said I recommend you do before you start doing the orbital diagram?
Your configuration.
The configuration. So in order to know which orbitals to set up, it helps to have that configuration first. So this one is that. So we have our orbital diagram. Okay, so our orbital diagram, when you set it up, it looks something like that. How many electrons are going to go in each of those? We're just going to make this easy. Are any of those not going to be full?
No.
No, they're all going to be full for this one because they're full up there. So we're going to have this as our orbital diagram.
So you only have to worry when they're not full.
Right. Like, I think the next one I gave you is, yeah, the next one I gave you, one of them is not all full. Any questions on this one? Okay, so then the next one we had was oxygen. If you look at the electronic configuration for oxygen, it is that. So for this one, now when we draw out our orbital diagram, it looks, our sketch kind of looks like this. How many electrons are going to go in that 1s? 2. How many are going in the 2s? 2. And then in the 2p, how many are going over here?
Only 4.
There's 4. So what we're going to do, go through, you draw the 1 in each of those 3, then you can pair up that last one. So you would have 1 paired and 2 empty. 2 with 1, sorry, not empty. Questions on that?
You only do that for the P block?
Any of them. If you had, like, let's say you had sodium, or let's just say lithium, it's less drawing. So if you have lithium, the orbital or electron configuration for that one is that orbital diagram. 1s would have 2, 2s has 1.
I see.
So you can have, any of them can have just 1 electron in it. Okay, questions?
How did you determine the split electron?
When you fill it up, you always write 1 electron in each of the suborbitals first. So since there's 3 suborbitals here, I said, okay, I have 4 total, so I want 1, 2, 3. Then I go back and pair it up when I continue, so that would be 4. If this was 2p5, I would have drawn another right there. So you do the 3 first, and then you go back and start pairing them up. Okay, other questions? Okay, makes sense to y'all?
Yeah.
Okay. Let me see, make sure that I got all of the terms that we talked about. Okay. Okay, so then the next thing we're going to look at, and I kind of very briefly introduced this the last time. I mentioned how I was always looking at the periodic table for my my little double check there. So the periodic table actually helps us predict the electron configurations. When we look at the periodic table, we've kind of talked, I don't know, I think I've kind of mentioned offhandedly the term valence electrons.
Yeah.
Valence electrons, first off, what are those? When we say valence electron, what is that? The outermost energy level electrons. So they're your electrons that are the furthest away from the nucleus. So in magnesium, what are our electrons that are the furthest away from the nucleus?
3s.
Which one of those? The 3s2. And how do I know that? Just by looking at this. The highest N value, right? So when I look at, remember our principal quantum numbers, we have 1, 2, and 3. The one that has the highest of those is going to be the one that is the outermost. Those are our valence electrons.
But would it be 2 valence electrons or just 3?
We would have 2. So you're going off of the 2 right there.
Oh.
Now, in something like, well, let's just look at calcium just for practice again. Calcium, looking at it, what is my highest N level there? My highest principal quantum number, what is it going to be?
4.
The 4. So how many valence electrons do I have there? I have 2 as well. And this makes sense because calcium and magnesium are in which period or group, sorry, of the periodic table?
For the alkaline metal.
Alkaline metal, group 2, so there should be 2 valence electrons. So they all still kind of agree. What about lithium? How many valence electrons does lithium have?
1.
Oh, the valence
1.
electron.
Because the highest value is the second shell, and there's only 1 electron there. It's 2s1. So we have just this 1 electron. So that has 1 valence electron. When I get to things like, let's look at nitrogen. Okay, for nitrogen, if I look at my highest N value, which one is it? What's my highest principal quantum number here?
5.
The principal quantum number.
The 2.
The 2, right? So I have 2 different shells that have the principal quantum number of 2. My valence electrons are the sum of those. Oops, sorry, I did that. That's not right. That should be 3. Right there. Sorry about that. So it's the sum of those two numbers. So when I look at this one, I add my s electrons and my p electrons, and how many valence electrons do I then get? 5. 5. According to looking at the periodic table, N is in group 5A, so how many valence electrons should it have? 5. 5, so we agree. So this kind of is another way, once again, of checking to make sure you're doing everything right. Now let's go down to something like, let's do bromine. Everyone draw the electron configuration for bromine real quick. Make y'all think a little bit. How many electrons does bromine have?
35.
35. Okay, so you should have come up with something like that. How'd we do? Any questions on that? Okay, so for this one, we're looking once again to determine the number of valence electrons. What is my highest N value here? 4. So notice that I have 2 of these with 4. And I add those together. So how many valence electrons would I have?
7.
7. Don't let the fact that this is thrown in right here, when you fill them up like this, throw you off. If you need to visualize this in a way where you have the numbers written from lowest to largest, go ahead and rewrite this. So if you want to rewrite this, like that, so that you can visualize it a little bit better, that is perfectly fine. You can rewrite it in that order. That is fine. So over here we have our 7 valence electrons. Then the rest of these are what is referred to as our core electrons. So over here we have our cores. What are the core electrons? The innermost ones, right? Are core electrons involved in bonding? No, they don't involve themselves with chemical reactions, so we don't worry about those. So they tend to stay kind of hidden inside there. The valence electrons are the ones that are going to be involved in bonding. They're the ones that are responsible for a lot of the properties that each of these elements have. So those are the ones that we actually want to figure out. So
If there was, for example, 4D, would you also add that one?
no, D electrons you don't add. But you wouldn't have, if you have 4D, if you had a transition metal, even, let's see, let's say, like, let's do one that actually ends in D. Let's do that as an example. Okay, so let's do copper. Make sure it's not one of the bad ones. Changing that, let's do chromium. There's a couple exceptions in the periodic table, so I'm avoiding those. Okay, so let's look at chromium, which is 24 electrons. Okay, so if you look at the chromium, our last ones that we actually fill up are in the D shell. However, what do you notice about the number, the quantum number for that D shell? What is it? 3. 3. What do we have right here? 4. Now, remember that when we're talking about those transition metals, the charges of them can change. And so we can't really say with certainty that copper or chromium has 2 valence electrons, or it has 5 valence electrons, or I think 7 is another charge, 7 valence electrons. Those charges change around a lot. And it's kind of because of that configuration. Those d electrons, they're considered core electrons, but they're still pretty close to the outside. So you can't really say with certainty how many valence electrons that those have. So when we're talking about the valence electrons, we typically use the representative elements. We just go with the A group. We tend to ignore those transition metals because of that reason. And also, if we look at something, let's go with it. Let's go with copper real quick. If I look at copper, I'll show you this deviation here. Okay, so if I look at copper, if you fill them out in the order that we've talked about, what you would get is a 4s2 3d9. And what actually happens is it will not form that. It will actually form 4s1 3d10. Reason being, it's a lot more stable to have 10 electrons in this D shell than it is to have 2 in this S shell. So the exceptions are something that if you go on the 150, you have to memorize, but here I don't really hit them up too much. I kind of try and just skip them over. I think your text does mention them, but they're not something that's all that important to me in this class. So be aware that there are some exceptions to this, but for our purposes, I try to avoid those exceptions when we're going through in the class. Okay, now that I've thoroughly confused you all, probably. Ignore that. But it's good to be aware that there are exceptions.
I don't understand how, for example, fluorine, it has a charge of -1, yet it has 7 valence electrons. How does, like, when it bonds, it gives away 1 electron?
It gains an electron.
It gains an electron, but it...
Yeah. So it fills up when it...
Oh, because it gains it, so it has 8.
And it fills up that outer valence, the outer shell, and so that's much more content now. That's kind of the same idea behind that exception that I just showed you.
Right.
Same idea, and I think we talk about. I know we talk about Lewis structures. We might talk about that a little bit more detail this next chapter.
Yeah.
Yes.
How many valence?
For this one, yeah, you would just say 2, because you would go off of the highest in value. Which, like I said, I don't ask those for transition metals because they change, so you won't be expected to guess that. Okay, any other questions on this? Okay, so looking at the periodic table, when we go over the kind of the way, I'll re-go over this, the way to look to make sure that your periodic table confirms whatever your electron configuration is. When you are writing your electron configurations out, the way that you do this is know that the S block is this right here, these first 2 rows right here. So whenever you have something in an S1, you should have one of these elements. If you have something ends in S2, you should have one of these elements. If you have something that ends in P, your P block is this part right here. It's from your transition metals over to your noble gases. So this is our P block right here. If it ends in P1, it's going to be in group 3, P2, P3, P4, P5, and P6. So if that's the last thing you fill up, you should be looking over there. Your D block is in here in the middle. This would be D1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then this is your F block down here. So when you start using the F electrons and you end in something that's in an F, it should be either a lanthanide or an actinide. It should be down in these 2 rows. So you can kind of confirm what you're going through. As far as your principal quantum number, the highest one, if it is in this row right here, it should be 1. Here's 2, 3, 4, 5, 6, and 7. So you can go through and confirm what it is that you figured out to make sure it's right. So like if I look at magnesium, what is my highest principal quantum number there?
3.
3. And what is it? It's 3 what?
S.
3s2. So that means I should be in period 1, 2, 3, and I should go over s1, s2. There's magnesium. If I look at chromium, what's my high? Well, that's that one. But we end in the D, right? That's our last one. So for that one, our highest end should be 4. So it's 1, 2, 3, 4, because that's the highest end. Then I end in the actual D4. That was the last thing I filled up, so I should be in D1, 2, 3, and 4. These things are just nasty in the middle. So they always go off. Then if I go back, let's go back to calcium again. Calcium, what is my highest N value? 4, and it's 4 what?
S2.
4 S2, so I should go down 1, 2, 3, 4, and I have S1 and S2, and it's right there. What was oxygen's electron configuration? Go back to your notes. Look up oxygen. The highest N value for it was what?
2p4.
2p4, right? So we should come down 1, 2, and we go over to the p block, and we go 1, 2, 3, 4. So it confirms it as well. We did bromine. What was bromine? 4s2, 4p5. So I should be going down 1, 2, 3, 4, and I have the p's are the last one, so I should go p1, 2, 3, 4, 5. It's right there. So it's a great way to double check the work that you've done when you are looking at your electron configurations. I would not rely on it when you're trying to write them out. I would still use that. I would just double check it with the periodic table. That way you have 2 ways to make sure that you're doing it correctly.
Professor,
Yes.
you know how you found the valence electrons for bromine and it's the 4s2 and 4p5, so you add those?
You add the 2 together, yes.
Okay.
So the S and the P electrons, if they have the same N value over here, always get added together for valence electrons. Okay, how are we doing so far?
Okay, better.
This chapter is, it's one of those that you have to do a lot of reading to fully understand, and lots of just looking at it again and again and again. Okay, I'm going to get some pictures up here for the next section. Computer wakes up.
It was a good game. Like, good plays and stuff. No, I don't.
Like right here, you have to figure out the color, so
Yesterday, oh yeah. Yesterday I had my math class and I had to go through the whole thing with logarithms without a calculator. I was a mess. It took my calculator. Everything has a computer.
you know, the linear, trigonal,
Okay, the next section that you were doing for today has to do with periodic trends, and another tool that we can use with the periodic table, so another way of predicting things. So here, this is the periodic trend known as atomic sizes. What do you notice about this trend?
they decrease to the right and increase going down.
Decrease to the right, increase as you go down. These trends you need to memorize. These aren't something that you can just, it's like you just have to know these trends. But my question for you is, if you look at, let's just look at period 2. When we look at period 2, where are the electrons with the most mass located? The elements with the most mass, where are those located?
Oh, is there more that way?
To the right, right? So in group 2, in period 2, what element has the most mass? Neon, right? Okay, which one's the least mass? Lithium, but which one's the largest?
Lithium.
Why do you think that is?
The electron
The electrons aren't as nice and tight, right? Why would they be more spread out in something that has less mass?
Is it because of the electron?
Okay, let's think of the shape of or what an atom actually looks like. When we have an atom, so let's say we have lithium. What is in the center of that atom? The nucleus, which contains what? Protons and neutrons, right? So in lithium, how many protons are in lithium? Okay, so we have 3 protons, and how many neutrons? That's like 4 to me. So we'll say 4. Okay, so we have 4, and I'm going to do the Bohr model just because it's way easier to draw. So here we have our first orbital shell, and then we have here our second one. So on this, in lithium, how many electrons are there? 3, so we would have 2 here, and then we would have the 1 here, right? Then if we look at neon, neon has how many protons in its nucleus? 10. Okay, so it has 10, and how many neutrons? And then around it we have our orbits again. And this time, how many electrons does neon have? It has 10, right? So we have our 10 electrons here. So something like that. Okay, so when we look at lithium and neon, what do we notice about the number of orbits? So the number of orbits, how do we compare those? The same, right? This one has 1, 2, this one has 1, 2. So they have the same number of orbits. We have an n equals 1, and we have the 2. We have the 2. So they have the same number of orbits here. What do we notice about the nucleus?
That one has less and the other one.
This one has less. What does it have less of?
Proton.
Protons. Why would protons be significant when we're talking about the size of an atom?
Because the protons are what keeps the electrons.
The protons are what attracts those electrons in towards the nucleus. So here, we have 3 protons, and out here in the second orbit, we have an electron. Do you think this electron is going to be pulled in as tightly to those 3 protons as over here, we have electrons that are the same distance away, but we have 10 protons pulling those electrons in. So here you have a lot more protons attracting those electrons, whereas over here you only have 3. So there's less force here pulling those electrons in, so you have a bigger atom. Make sense?
Yeah.
Hopefully when it's drawn that way. So that's why the atomic size is kind of counterintuitive. It's like people have a hard time remembering that over on the right, even though they're more massive, they're actually a smaller atom. So when we're going with atomic size, our smaller atoms are on the right. As we go down, they tend to increase. Remember, when we go down, if we're looking at lithium versus like sodium, if this was sodium, I add on a whole nother orbit. So I've actually increased that size. So that's why when you go down, it makes sense because you're adding on another orbit, it does get larger. So you go down, it increases. When you go to the right, it decreases. Questions on that one? Now, what you should be able to do with this is to actually predict. I would ask you a question. You would have to tell me which one is a smaller atom. So I did this down at the bottom. We're going to skip to those, then we'll go back to ionization energy. So which one's smaller, mercury or TL? What is TL?
Thallium.
Thallium, thank you. So we have mercury or thallium. Which one is smallest?
Thallium.
And why is it smaller? I don't think mercury's on here, so that's good. Okay. So looking at that periodic table, where is mercury located? It's on 80. Where's thallium? 81. So which one is smaller?
Mercury. Oh, no, wait.
Thallium.
Thallium is smaller.
Thallium is smaller because it's further to the right, right? So you go further to the right in the same period, and it's going to get smaller. Okay, questions on that one? Okay, then we have B. What's GA?
Gallium.
And then ion?
Indium.
Indium. Which one's smaller?
Gallium.
Okay, so if you look at your periodic table over there, gallium and indium are located in group 3A. They're both in the same group. But as we go down, we increase in size, right? So since gallium is above indium, that means it's going to be smaller. Questions on that? Now, your textbook likes to be tricky sometimes. And you're going to get these kinds of questions. I do not give you these kinds of questions on the test. It doesn't matter what textbook you look at, though, they do this. They'll say, which one's smaller, sulfur or bromine?
You can't do it.
So when you go down, they're supposed to get larger, right? But when you go to the right, they're supposed to get smaller, right?
Yeah.
So when you go diagonally like that, can you tell based on the information that you have?
No.
No, you cannot tell. If you look at this, so they look pretty much identical to me. My eyes cannot tell a difference. And I know this isn't to scale, but it's kind of hard to tell. So sometimes you'll be given that problem and you would just say like not enough information or not possible to determine, something like that. You can't actually choose a correct answer. I don't do those on exams because they drive me crazy. So don't worry, but just be prepared when you're doing the homework, you will come across some of those. Okay, the next thing is looking at ionization energies. Okay, so ionization energy, first off, what is it?
The amount of energy required.
The amount of energy for an element to ionize. So is that gaining or losing electrons? Because they're different.
You're removing it.
You're removing it, right? You're making it an ion. So you're making it like sodium ion, potassium ion, something like that. So with ionization energy, you're looking at when you're forming a positive charge. So based upon what we know on the periodic table, which elements are going to be the easiest to ionize? The alkali and the alkalines. So we already know metals form cations, right? So when we're talking about ionization energies, we're talking about positive charges. So metals are going to ionize more easily than your nonmetals. Have you ever heard of a Cl1+? No, it's really hard to get to that stage. It takes a ton of energy. So when you look at that right-hand side of the periodic table, the nonmetals, you're going to have very high ionization energies. On the left-hand side, you're going to have lower ones.
Why does the book say energy required to move an electron from the atom in a gaseous state?
Yeah.
When they're ionizing things, they're using an element that's in the gaseous state. So they calculate this based upon it as a gas. That way they're all consistent because you have, otherwise if you do something as a solid, it's going to be harder to ionize than if something is in a gas. It's just part of the stability, the way it works. So this way they're consistent throughout every element. So you're not comparing apples and oranges, you're comparing apples and apples. Okay, so let's see here. Ionization energy. So here we have our trends with ionization energy. It increases as you go to the right for reasons we just kind of mentioned, and it decreases as you go down. Okay, so let's look at this on the molecular level. So if we have something like, we're just going to do lithium because it's so much easier to draw. If we have our lithium, so here we have lithium, we have our 2 electrons in the inner, and then we have our 1 electron out here. In order for these to be content, they want their outermost shell to be full. So for lithium, in order for this second shell to be full, how many more electrons would it have to gain? 7. If it gets rid of 1, though, it would have a full shell of electrons for its outermost shell. So lithium really has motivation to get rid of that 1 electron. That's why it's so reactive. So it just gets rid of that 1 electron. It's really easy, and it gives it away pretty freely. If we look at chlorine, or let's do chlorine. How many electrons does fluorine have in this outer shell? 7. It wants to have 8 in that outer shell to make it content, right? So for it only has to gain 1 electron. So it's going to want to gain that 1 electron really easily. Ionization energy, remember, is what we're removing electrons with, though. It's saying that you're getting rid of them. So if I was going to get rid of electrons to get to my next full shell, how many electrons would I have to get rid of here? I'd have to get rid of 7. So I'd have to get rid of all 7 of these electrons to get to a full shell. So it takes a lot more energy to yank all those 7 electrons out. Those electrons do not want to budge. That's why the electron energy for fluorine would be so high. Now, so that's kind of our left to right picture. As we go down, okay, as we go down, we say that the ionization energy decreases. Same concept that we talked about before. As we go down here, we are increasing the size of the shell. So here, this last shell is further away from the nucleus. So we have increased the size, it's further away. There is less pull on this outermost shell of electrons. So this electron will be easier to yank away than this one that is closer to the nucleus. So as you get further out, you start adding the number of shells and orbitals on, then you're going to make it easier to pull those electrons away. So the ionization energy actually decreases as you go down. So where is our highest ionization energy element on the periodic table? Which one has the highest? Yes. So helium is going to be the highest. Which one's the lowest?
Well, it
It
decreases.
decreases as you go down.
Is it
Fr is francium, yeah. So our highest is at the top right, lowest is down at the bottom left. Okay, so when we look at our problems here, we want to know which one has the highest. Is it going to be silver or gold? Which one?
Silver.
Silver. So when you look at these, if you look at silver and gold are over in the transition metals group 1B. Silver is higher than gold, so based upon what we've talked about, silver should have the higher ionization energy. Question on that one. Okay, then we have copper or silver. Copper. Okay, questions on those. Once again, be prepared for the you don't have enough information to tell. It happens on these as well. Okay, and then our last trend that we're looking at is metallic character. What do we mean by metallic character? How much it acts like a metal, right? So metallic character is basically just what it sounds like. Okay, so when we look at metallic character, here we go. These are our metallic character trends. This should make a lot of sense. The metals are located on the left of the periodic table, so most of the metallic character as you go left is going to be a lot. As you go to the right, it's going to decrease. So your metallic character is greater on this side, less on that side. And then metallic character also increases as you go down. So when you go down, it increases. As you come to the right, it decreases. So for this one, the problems that we had here, silicon or sulfur, which one of those is more metallic? Silicon. Silicon is in group 4A, whereas sulfur is in group 6A. So we have the 4A group is going to be more metallic. And then what about chlorine or astantine? Okay, and why would astantine be more metallic? It's further down, right? Okay, questions on that? All right, so the biggest thing with these is to not confuse them. So when we summarize these, our atomic size, what happens with atomic size as you go down?
Decreases.
As we go down, atomic size increases, right? And as you go to the right, what happens?
Decreases.
Decreases. When we look at ionization energy, as you go down, what happens? It what?
Decreases.
Decreases. And as you go to the right, what happens?
Increases.
Then when you have the metallic character, as you go down, what happens?
It increases.
Increases, and as you go to the right, what happens?
It decreases.
Okay. So make sure you keep those straight in your mind. So you should see that atomic size and metallic character are very similar. It's the ionization energy that you really need to be careful with because it's the opposite. So don't confuse all those and start predicting everything wrong. questions on this?
Professor, on the ionization, you know how you said which one has Hamarites and francium, what was it, had more or less?
Francium for ionization energy, that should be the least one.
Okay, so what happens if you go down to like lanthanide?
The lanthanides and that's a great question. Where do the lanthanides and actinides fit in on the periodic table?
After the lanthanide event.
Right here, right? So you could plug those in, you just kind of shift this up right into here, expand that out. And so they would just come in here. They plug in right here. So it's the same thing. As you would go across them, in this case, as you would go from left to right, the metallic character would decrease, atomic size would decrease as well.
Okay,
So they just kind of plug in right there.
okay, because I was trying to, when I said francium, I was like, the other two are going down.
Yeah,
But
it's just because they
go
pull them
out.
out.
So I gotta like, just like, put it like a puzzle.
Yes, just put them back in there and
Okay.
visualize it that way. Other questions on that? Okay, let's start going over some of chapter 10 then. So chapter 9's good. You guys are all going to ace it?
Yeah.
At least you have a sense of humor about it, right?
Well, it's like a game.
Okay. This next chapter is on Lewis structures, and Lewis structures, we've very briefly talked about these several chapters ago. I kind of introduced the concept when we were talking about ionic bonding, covalent bonding. But we're going to look at this with a lot more detail now, and actually the lab this next week is going to be on Lewis structures, where all you're doing is drawing Lewis structures all out. So it's something that's pretty heavily emphasized, and it's important to understand. Okay, I'm not going to go through the whole outline because I'm leaving some for y'all to fill out, but I'm going to go over the main points of this for starting, and we'll just kind of work through it. When we are looking at compounds, remember that we have two different types of compounds. We have ionic compounds and we have covalent compounds. What was the difference between ionic and covalent compounds?
Ionic is a metal and a non-metal.
Ionic's metal, non-metal. Covalent is what? Two non-metals. When we wrote formulas for these, with ionic compounds, what did we use? How did we write their formulas? What did you have to know? You looked at the periodic table and you figured out what?
They're charged.
They're charges. So we use charges for these. So if I'm using charges, what does that mean that they're doing with electrons?
They're transferring.
They're transferring. Yeah, one's giving electrons to the other one's taking them. There's this transfer of electrons. Whereas with covalent compounds, we never mentioned charges. We left this out. I said, don't worry about charges. They don't work that way. What they do is they actually share electrons. So covalent compounds share electrons, and that is where the emphasis of Lewis structures actually hits. It hits the covalent compounds. We will briefly discuss ionic compounds, but most of the time will be spent on covalent compounds. With atoms, we said that they have valence electrons, and they want to form a full outer shell. So we have these terms that we call an octet and a duet. Duets are just like they sound. How many electrons do you think are in a duet? Two. Duet.
Oh, duet. I'm thinking.
Yeah, like
sorry.
a duet.
I'm thinking of
Duet. So a duet has two electrons in its outermost shell. There are two elements in the periodic table that will ever want to form a duet. What do you think they are?
Helium.
Helium and hydrogen. Those are it. Everything else does not want to ever form a duet. So we have helium and hydrogen will form duets. This means that their outermost shell has two electrons in it. That's a duet. Helium naturally forms a duet. That's its noble gas state. It has two electrons in it. It's perfectly content. It doesn't need any more. If you have something that is anything other than that, just about anything other than that, I'll say, it forms an octet. What does an octet mean?
8 bit.
8 valence electrons. So it has 8 electrons in its outer shell. This is what we call our noble gas configuration. All the noble gases have 8 valence electrons, so they're all perfectly content. Everything else in the periodic table does not, so it's trying to achieve that. Oh, I lied. Lithium will have 2 valence electrons as well. It will form a duet. Okay, so an octet would be something like, let's just say, nitrogen. If nitrogen wants to have a full outer shell, it will form something with 8 valence electrons. So it forms an octet. It gets 8 electrons in that outermost shell. So we do this with them by either sharing electrons or by giving or gaining electrons. So when we're looking at nitrogen, it depends on the type of compound it's involved with. If it's involved with an ionic compound, you have this transfer. If it's involved with valent, we're going to have sharing. But the desire, the final goal here is that they somehow get 8 valence electrons. That's our octet. Okay, so let's start with the structures of ionic compounds and looking at the Lewis dot structures for those. And we have talked about these in the past. It's just been a while. So with ionic structures, once again, we recognize them by looking to see if we have what?
A metal and a non-metal.
A metal and a nonmetal. So you see a metal and a nonmetal, you know you have an ionic structure. We have electron transfer with ionic compounds. So let's say, for example, we'll just look at the first one that's down here. We have CaS. When we're looking at calcium sulfide, we know that we have 2 ions because we have a metal and a nonmetal. What is the charge of calcium? Ca2+. What is the charge of sulfur?
Minus.
2-, right? So what does that mean? They cancel, but what happens? If I'm looking at the electrons from start to finish, what happens to the electrons?
They transfer to each other.
They transferred from which element?
From calcium.
From calcium to where?
Sulfur.
To sulfur. So they left calcium, went over to sulfur. So if I look at calcium, my calcium element sorry. Okay, so calcium, the diagram looks something kind of like this. Sulfur, if I look at it, it looks something like this. So when I look at calcium, my outermost orbit there has how many electrons in it? It has 2. So I have 2 electrons here, but according to my octet rule, how many do I desire? 8. So once again, is it going to be easier to lose 2 or to gain 6? It'll be easier for it to lose the 2. If I look at sulfur, how many electrons are in that outer shell? 6. So for that one, is it easier to lose 6 or to gain 2?
Gain 2.
It'll gain 2. So it takes these 2 outermost electrons, and they come in, and they leave calcium, and they come over here to sulfur to fill in that octet. So this one now has a full outer shell. This one now has a full outer shell. So they're following the octet rule there. So this is kind of the concept behind how these ionic compounds form with the electron transfers that are involved here. When you draw the Lewis structures, I'm going to leave that to you guys to read up on. But just be careful about forgetting to include charges. Make sure you include charges on them. That's a very common mistake. So you guys can fill that out and we'll go over it next Tuesday. But my hint is charges. Remember the charges. So scribble that down next to it if you need to. Don't forget to write them in. Okay.
Question.
Yes.
Calcium, would you remove the outer shell? Is that no longer there anymore?
The shell is still there. It's just empty.
Okay.
Yeah. And this is, you have Thursday lab, right? Yeah. What you'll see in lab today is that there's actually, it's not that the orbits and the orbitals, I should say, just magically disappear. They're just not used. So, and we'll show that today in lab. You'll actually see that transitions can still happen past that. It's just they're not used in the ground state. Okay, other questions on that? Okay, so let's go on to covalent structures then. So practice those, and you have to draw them using this theory as well. So you'll be using this octet rule to try and predict two problems as well. Hopefully I didn't do this. Okay, with covalent compounds, how do you recognize that you have a covalent compound? When you look at naming, when you say, okay, it's dihydrogen trifluoride or something, how do you know to name it that way? I don't know if that will exist, but hey, whatever. It's two nonmetals, right? So we have two or more nonmetals in these covalent compounds. So when you see two or more nonmetals, you know you have a covalent compound. Drawing Lewis structures for those is different than this. You do not have ions forming. So you don't sit there and try and figure out ions and figure out transfer of electrons. It's done differently. When you have covalent structures, we have sharing of electrons. And there's a few different ways that we can actually share electrons. So we're going to start off by looking at the simplest covalent compound that there is, NH2. H2 is two hydrogens that are bound together. How many valence electrons does hydrogen have? So how do we determine this just looking at the periodic table? What can I look at to tell me how many valence electrons it has? My group number. So I just look at the group it's in for the A group elements, which all nonmetals are A group elements, and I can know how many valence electrons I have. So hydrogen has how many valence electrons? 1. So this one has 1, but it wants to have access to how many? 2. So you bring in another hydrogen with 1 electron, and these share those electrons. So they each have access to both electrons. So this could be rewritten like that. That is H2. They're sharing those 2 electrons. If I have something like HCl, we know hydrogen has 1 electron. We just said it. How many does chlorine have? What group is chlorine in? Group 7, right? So how many electrons does it have? Valence electrons? 7. So for chlorine, I have my 7 valence electrons. Hydrogen wants how many more electrons? It wants 1. How many does chlorine want? 1. So what they'll do is they will share those 2 electrons right there. They each have access to them. This one now has access to 2. Chlorine now has access to 8. So we write this as HCl. Questions on that? Okay, now when you are drawing these Lewis dot structures, remember, I think we talked about them at all. Have we ever talked about Lewis structures in here with covalent? Okay. When you're drawing these, it's kind of the same concept that we just went over with orbital diagrams. When you're drawing an element by itself with its electrons, you draw in the first 4 electrons on each side of the atom first, and then you pair them up. So like hydrogen was 2. Lithium has 1, it's drawn like this. We have beryllium has 2, it's like this. Boron is 3, looks like that. Carbon is 4, it would look like that. You draw them 1 on each side first. Once you get past 4, now you can go through and pair them up. So if we have nitrogen, it would look like that. Oxygen is like that. And chlorine looks like that. And then neon is all paired. So it is important to make sure that you draw them correctly, because that will change whatever you end up with as your final answers. So the filling order there is kind of necessary to learn. Okay, so back to this. We have, this is the sharing of 2 electrons. These right here, when you're sharing only 2 electrons, are what are known as single bonds. So whenever you have a single bond that's formed, there's only 2 electrons involved in there. Let's say I have something like oxygen. Oxygen has how many electrons? Valence electrons. It has 6, right? So oxygen has 6 valence electrons. If I have O2, I have 2 oxygen atoms that each have 6 electrons. How many electrons do they want to have? 8. How do you think they can achieve that? They'll share 2 sets of electrons, a double bond I heard. So they'll share these ones right here and these ones right here. So oxygen can actually share a total of 4 electrons. So we would have this, where this thing in the middle right here is not an equal sign, it's actually just a double bond. So double bonds, you're sharing 4 electrons, single bond, you're sharing 2 electrons. So how many electrons do you think a triple bond shares? 6. So something like nitrogen, if you look at nitrogen, how many valence electrons does it have?
5.
It has 5, so we draw nitrogen. 2 nitrogens like that, they want to have how many more electrons each? 3. So they're going to share 3 sets of electrons. So you'll have, I'm going to change the way to do this, make it a little easier. 1 shared here, 1 shared here, and 1 shared right here. So you would just redraw this as that. And here is our triple bond. There is not a quadruple bond. Yeah, carbon will do lots of funny things, but it doesn't do a quadruple bond. So there's usually, you can do like 1 single, 1 triple, you could do 2 doubles, you could do 4 singles, there's different combinations, but it won't do like quadruple. Yes?
Does it matter when we have the leftover electrons? Like for oxygen, I have 2 on top and 2 on the side.
Like you did like this?
Yeah.
I would not dock you for that. Naturally, the electrons are going to try and minimize their distance to each other, so they would get as far away from each other as possible. But as long as you have them paired like that, that will be fine. So I would not penalize you for that, per se. When we get to Vesper, which if you haven't been in your outline yet, you know nothing about it. But when we get to drawing shapes, when we're drawing the actual shapes of the compound, then it will matter. But for this, it does not matter. You guys are going to love Vesper. Okay. You don't trust me. No one's sitting there looking excited. You're all sitting there going,
That's the worst thing ever.
okay. When we are looking at single, double, and triple bonds, there are certain properties that are changed based upon what kind of bond you have. If you had to guess, what bond do you think is the strongest, the single, the double, or the triple? Triple. Triple. Triple bonds are much stronger than single bonds. They're harder to break. It's a much more stable compound. They're also shorter. So triple bonds, they're going to bring that compound in closer together. So the atoms are going to be closer together. So triple bonds, they're stronger bonds. Just keep that in mind because we're going to talk about their properties in a few chapters. And let's see here. So you asked about the location, which is great. Don't forget to draw those extra electrons. That's a common mistake. People don't put them in. We have what are known as shared and unshared electrons. The shared electrons are the ones that are actually involved in the bond. The unshared electrons are those that are the lone pairs, depending on what you see, are the ones that are surrounding just the one atom. So know the difference between those terms as well. Okay, and I think I'm going to stop there because there's no way to do my next part, and you guys can write up all the stuff. Never say I don't let you have keep you 30 minutes today.
So
I tried.
I'll remember that for Christmas.
Oh, thank you.
Yeah.
Here's your 1 cent tip, right?
Don't spend it all on